This video is on the mean value theorem and Rolle's theorem. So, Rolle's theorem says, let f be a continuous function on the interval ab and differentiable on the open interval ab. If f of a equals f of b, then there exists at least one number c in ab where the derivative of c is equal to 0. If these conditions hold true, then there's at least one number between a and b so that the tangent line is horizontal, which is what the graph is showing you. So make sure you highlight that box, because that's an important theorem. Alright, but the really important one is the mean value theorem. It's kind of as important as the intermediate value theorem, which was on your final, which we're going to go over when we get back. But the mean value theorem says if f is continuous on the closed interval ab and differentiable on the open interval ab, then there exists a number c in ab such that f prime of c equals f of b minus f of a over b minus a, which, if you remember, that's the same thing as a rock, which is the average rate of change. And verbally, that's saying that the instantaneous rate of change is equal to the average rate of change. And graphically, it's saying that the tangent line is parallel to the secant line. So make sure you highlight that box as well. And rather than saying the mean value theorem all the time, we're going to call it the M.V.T, which stands for mean value theorem. So, example 1 says, let f be the function given by so-and-so. Find the number c that satisfies the conclusion of Rolle's theorem for f on -3, 1. So first, we need to find the derivative, which would be 2x plus 2. We set it equal to 0. We can actually factor out a 2. And we get x is equal to -1. Well, from now, if we find the regular function and we substitute in 3, we actually get 0. When we take f of 1, we also get 0. -3 and 1 are the values of the closed interval that we're given. So, in this case, the derivative was equal to 0 at -1. The regular function was equal to 0 at both -3 and at 1. So, we have already found our number c that satisfies the conclusion of the Rolle's theorem for f, which says that if f of one value is equal to f of the other value, meaning they're both equal to each other, there's a number in between those two where the derivative will equal 0. And in this case, that number is at -1. And that's it for example 1. Example 2 says, at what values on the interval -2, 3 does the graph of the function satisfy the M.V.T? Well, it's actually laid out the steps for you. First, you need to find the derivative, which is 2x plus 2. They want you to find f of -2 and f of 3. So f of -2 will be -2 squared plus 2 times -2 minus 1, which is equal to -1. F of 3, 3 squared plus 2 times 3 minus 1, and that's equal to 14. Step 3 says apply the definition of the mean value theorem. Well, the definition of the mean value theorem is find a rock and set it equal to your derivative. Well, the derivative we got was 2x plus 2. We're going to set that equal to f of 3 minus f of -2, all of it divided by 3 minus -2. So we end up with 2x plus 2 equals 14 minus -1 divided by 5. So 2x plus 2 equals 15 over 5. 2x plus 2 is equal to 3. 2x equals 1. And x equals half. And that's what you were looking for. And that's it for question 2. Question 3 says, a sports car speedometer registers 50 miles per hour as it passes a mileage marker. 4 minutes later, the car passes a marker that is 5 miles from the first, and the speedometer registers 55 miles per hour. Can you use the mean value theorem to prove that the velocity of the sports car was more than 70 miles per hour at some point between the two mileage markers? So, first of all, we're going to let t equal the elapsed time in hours after the car passed the first marker. And S of t will be the distance in miles from the first marker at time t. And our time was, 4 minutes later, so 4 over 60, which is the same thing as 1/15 of an hour. So the question is asking us if we can use the mean value theorem, which is the A-rock formula. So if we actually draw it out, A is the first marker, B is the second marker. Time here is 0, and time here is 1/15 of an hour, which is the 4 minutes that have passed. And S of t is the distance after it passed the first marker. Well, mean value theorem is just A-rock, so the average velocity is going to equal to S of 1/15 minus S of 0 over 1/15 minus 0. Well, S of 1/15 was that it was 5 miles ahead of from where it started, minus the initial one, which we're saying is 0, so 5 minus 0 is just 5. All of it divided by 1/15. A number divided by a fraction, you multiply by the reciprocal. So you really end up with an average velocity of 75 miles per hour. So in order to answer this question, yes, we were able to use M.V.T. to prove that the velocity of the sports car was more than 70 miles per hour at the time between the two mileage markers. So here would be our answer, and we are done. Example 4 is telling us, given this function, find all values of c in the open interval 1, 4 that's guaranteed by the M.V.T. So first we have to find the slope of the secant line, which is finding A-rock. So we do f of 4 minus f of 1, all of it divided by 4 minus 1. 5 minus 1 is 4, minus 5 minus 4 is 1, 4 minus 1 is actually 3, so we end up with 3 over 3, which gives us a slope of 1. And it says, does f satisfy the conditions of the mean value theorem? And we're going to go with yes, because f is continuous and differentiable on the open interval 1, 4. Step 3 is asking us to find x such that the derivative of f of x is equal to f prime of c. So we need to find the derivative. So the derivative in this case is going to be 4 over x squared, and we're going to set that equal to f prime of c, which in this case we found out was 1. And 1 as a fraction is 1 over 1. Cross multiply, we end up with x squared equals 4. X is going to equal to plus or minus 2. And the only value from the plus and the minus 2 that falls in between that interval is positive 2. And that's the one that satisfies the M.V.T. on 1, 4. Now, it's important to state that M.V.T. is important because it allows us to identify exactly where graphs rise and fall. If functions have positive derivatives, then they are increasing functions. If they have negative derivatives, then they are decreasing functions. So that's one of the advantages of M.V.T. Example 5 says, find local extrema and intervals on which f of x is increasing and decreasing. So step 1 says find the critical numbers. If you remember from the last video, to find the critical numbers, you find the derivative, you set it equal to 0. So f prime will equal to 5 minus 2x. You set that equal to 0. And that gives you x is equal to 5 halves. Step 2 says set up the intervals determined by critical numbers and test signs of f of x. Well, the only critical number we found was 5 halves. So if we draw out a table and we start off with our critical number, which is 5 halves, we have to pick a number smaller than 5 halves and a number greater than 5 halves. Well, let's use x equal to 1 and x equal to 3. And it can be any number smaller than 5 halves. I just decided to use that one. Well, if we substitute these values into our derivative, when we substitute in 5 halves, our derivative will equal to 0. If we substitute in 1 into our derivative, our number is a positive, so it's increasing. If we substitute in 3 or bigger, they're actually negative numbers, which means it's decreasing. So, and I just stated step 3, determine the behavior of f of x. Well, f of x increases on negative infinity to 5 halves, and it decreases on 5 halves to infinity, which means that the local extrema on this point, if you look at the table, means that when x is 5 halves, we have a maximum. And really that maximum value is the y value that we get when we substitute in 5 halves into the original function, and that is 6.25. Let's go on to example 6. Find all values between the x-intercepts for which Rolle's theorem holds for the roots of f of x, and it says verify with your calculator. Well, first we have to find the x-intercepts, or the roots, to this function, which means we have to set the function equal to 0. So 4x squared minus x to the 4th equal to 0. You can take out an x squared. Set them equal to 0. Actually, a negative x squared. Oh my goodness. My bad. That was actually a minus. Let me fix that. Okay, so that's x equals 0, x equals 2, and x equals negative 2. And these are your zeros. Now we're going to find our critical numbers, which means we got to find the derivative. In this case is 8x minus 4x cubed. Set that equal to 0. We can take out a 4x. We're left with 2 minus x squared equal to 0. X will equal 0. And x will equal plus or minus the square root of 2. And these right here are your critical numbers. And then Rolle's theorem stated that if on the intervals they equal to 0, then there is some numbers that fall in between in which the derivatives will be 0. Well, square root of 2 is going to be in between 2 and negative 2. And the derivatives of this one are equal to 0, so then Rolle's theorem will hold true. And let's show it graphically. So we've got x, we've got y. We've got our zeros. Two, 0, 0, 0, and negative 2, 0. And in between those, we have negative square root of 2 and positive square root of 2. Because the polynomial is even with a negative leading coefficient, if you remember from algebra 2. It's going to go down, then it's going to go back up, and then it's going to come down, and then it's going to go back up, and then it's going to go straight down. So you actually have maximum values here, which in this case are the negative square root of 2 and the positive square root of 2. So, in conclusion, we're going to say that Rolle's theorem holds for x equals 0 plus or minus the square root of 2 between the x-intercepts of f of x. And let's verify it with the calculator. There's your graph. Maximums. So we gotta find our lower bound first. And if we can drag that down, it actually gives us negative 1.1412. We check that on the calculator. It's the same exact thing, so it's true. Example 7. Explain why the mean value theorem cannot be applied to the given function on the interval. Well, first, to apply the mean value theorem, we need to find the derivative of the function. So in this case, that's 2/3 x to the negative 1/3. And then I believe when x is equal to 0, our derivative will not exist because you can't divide by a 0. And this is the same thing as 2/3 x to the 1/3. So now, if we do a rock, we're going to do f of negative 5 minus f of 5 divided by negative 5 minus 5. And we're going to set it equal to our derivative that we found. We're going to have negative 5 squared is 25, so we're going to have the cube root of 25 minus 1 minus, again, the cube root of 25 minus 1, all of it divided by negative 5 minus 5, which will be equal to our derivative. Well, the top will cancel out, so we're left with 0 over negative 10. Which is equal to f of x. Well, 0 over negative 10 is the same thing as 0. But originally we found that f prime of x did not exist. So it cannot exist and also equal to 0. So therefore, that's what these 3 dots mean. The M.V.T. cannot be applied to f of x on the interval since the derivative did not exist at x equals 0 on the interval. And that's it for Rolle's theorem and the mean value theorem.